Good afternoon. Today we are going to see about thermodynamics and heat transfer. In thermodynamics and heat transfer, we are going to see about the forced convection problem. In forced convection, the changing of heat and the transferring of heat from solid to liquid or liquid to gas. There is a medium in between solid to gas or liquid to gas or solid to liquid or liquid to solid. So in this medium, we are going to find out the heat transfer or heat loss. So for the same, it contains three flows, that is laminar flow, turbulent flow and fully developed turbulent. So this is the example for fully developed turbulent flow from the leading edge. So initial start ஆகிற விஷயத்துல இருந்து ending முடிகிற வரைக்கும் it is considered as the turbulent flow. So we are going to see about the question for this problem. For a particular engine, the underside of the crankcase can be idealized as a flat plate measuring 80 cm across 20 cm. The engine runs at 80 km per hour and the crankcase is cooled by air flowing past it at the same speed. Calculate the heat loss from the crank core surface temperature of 75 degrees Celsius and the ambient air temperature is 25 degrees Celsius. Assume the boundary layer becomes turbulent from the leading edge itself. In this video, the question will be highlighted in front of this video. So the given data is area, that is 80 cm into 20 cm. That is, we have it is length and breadth. The crankcase is the bottom of the engine. So it is in length and breadth. So 80 cm into 20 cm. That is 1600 cm square. We have to convert it into meter square. So converted at meter square is 0.16 meter square. So then velocity at the flow or this is forced convection. So velocity is mentioned. So it is a way to find out it is a forced convection or free convection. So U is given, that is velocity 80 km per hour. I have to convert it into meter per second. That is 22.22 meter per second. So that the surface temperature of the crankcase is 75 degrees Celsius and the surrounding air temperature, that is ambient air temperature is 25 degrees Celsius, that is T infinity. In the question it is mentioned that the flow is fully turbulent, the flow is turbulent from the leading edge, so it is considered as the fully turbulent flow. We can use the HMT data book in the page number 124 of 10th edition. The fully turbulent flows value is there. So we will take the formula of this fully turbulent flow. So we have to find the heat loss Q. And the first step is we have to find TF. That is fluid temperature. That is W plus T infinity divided by 2. So 75 plus 25 divided by 100 divided by 2 is 50. So we can take the properties of 50 degrees Celsius from 45 page number of HMT data book. So we can take kinematic viscosity, thermal conductivity and the rho and the PR, Prandtl number. So these values are available in page number 45. We can take for 50 degrees Celsius. First, we can take the properties for 50 degrees Celsius, kinematic viscosity, thermal conductivity, density and Prandtl number. By using these values, we can substitute in Reynolds number. So the Reynolds number is UL divided by B. So why we can take UL instead of UD is it is a crankcase that A is given as length into breadth. So velocity into length divided by kinematic viscosity B. We substituted all these things and we get 9.9 into 10 to the power 5. So in the question itself they mentioned as it is a turbulent flow. You are not supposed to find out the Reynolds number or all. So procedure of the step to get the marks and all, we have to find the Reynolds number. So the flow is turbulent. So in the question it is says the flow is turbulent from the leading edge. So it is a fully turbulent from the leading edge, starting level ending value it is a turbulent. So there is a flow turbulent to fully turbulent difference is there. So from the page number 126 from the data book we can take NUX. So this is mentioned as local Nusselt number. So we find out all these things. See, so we substitute all these things, we will get NUX. So by using NUX, 1645.4 substituted in HXL divided by K. So it is a local average Nusselt number to find out the average heat transfer coefficient. So that is Hx. It is also available in page number 123 of 10th edition HMD data book. So Hx is equal to 58.12. So if it is a laminar flow, H or formula is 2 into Hx. So it is a turbulent flow now 1.5 into Hx. So it is fully turbulent flow. So it is H equal to 1.25 into Hx. So substitute the Hx value, we can get H. So by using Q is equal to HA TW minus T infinity, that is overall heat transfer coefficient, area, surface temperature and air temperature, surrounding temperature. Substitute all the things HA and TW minus T infinity, we can get 581.2 watts. So this much of heat is lost in the crankcase by giving this ideal constant cycle with following data. So it is a flow, is fully turbulent. So this is the example for the fully turbulent flow. Thank you.